Hi everyone, welcome back to the Data Idols Summer School. Welcome back to everyone in the community who has been supporting us for the last 5 years. I'm Adam, I'm a technical recruiter here at Data Idols. The Summer School is a new pilot programme in partnership with the Data Science Festival. It will run live for 3 months, so you can learn in real time and pick up new skills from the comfort of your own home. These sessions are designed for people transitioning into data, starting their career in data, and graduates and such like. So you can all get involved in the community by using our Slack channel. You can basically go onto the Data Idols SS Slack channel for any event related questions, comments or feedback. I'd also like to thank our partners who have made this event a real success, and also to the team that have put in over 400 hours to make the summer school a reality. All these sessions are pre-recorded and can be watched back at a later date starting in September. We'll be emailing you a link to watch all the sessions back, and they'll be free to watch. So anything you want to learn or anything you've missed, you can watch that back at your own pace. So today's session is an introduction to linear algebra. That is with Antonio Campello from Wellcome Trust.
Hi, my name is Antonio Campello, and today you're going to be talking about linear algebra. I'm going to be teaching you some of the important concepts, terminologies, and theories behind linear algebra that you will encounter during your data science life. And I'm also going to describe some of the coolest applications of linear algebra. A little bit about myself. I did a bachelor's degree in mathematics, after which I completed an internship in cloud storage and went on to do a PhD in applied mathematics using a lot of linear algebra, a lot of probability theory, a lot of information theory. And as a matter of fact, my first academic paper was in a journal called Linear Algebra and Its Applications. After that, I went on to do a couple of postdocs in applied mathematics, working mainly on the reliable and secure communication of data. So those are 2 books that I contributed to. And after that, I went on to have 5 years of commercial experience in data science, working on things like computer vision. Here's a picture of a project that I did on coral reef segmentation, and natural language processing, time series, and optimization. And I hope today I'll be able to share some of my knowledge with you. And one of the most compelling stories of why I think linear algebra is important for data science is the one of a friend who was transitioning into the field of data science, and he was starting to do a project on finding similar texts to a data set. So he had a very big data set and he wanted to find which texts are the most similar to each other. So after doing some research, he finds out that he has to do some transformations with the text. And after that, he has to compute something called the cosine similarity. And he goes on Google to try and find what is the cosine similarity. So he finds the documentation of this very famous package in Python called scikit-learn that describes the cosine similarity. So he tries to read what exactly the cosine similarity is. What is it doing on your data? So the documentation says, the cosine similarity is the normalized dot product between 2 matrices. He doesn't quite understand what this is. When he goes on to see the formula is also a bit cryptic. There's quite a lot of symbols, quite a lot of things going on there, as well as the explanation of the formula that says that on L2 normalized data, this is the same as a linear kernel. So he ends up more confused than he was before. And the reason why he was confused was that because he was not very familiar with the terminology of linear algebra. So the objective of this talk is to teach you some of the main terminologies, the main notions and concepts of linear algebra that will enable you to understand core data science algorithms better And hopefully after this talk in the future, you'll be able to read documentations like these. So today we're going to be looking at vectors, which are the fundamental building block of linear algebra. And with vectors, you can do dot products, calculate the norm, calculate the angle. After that, we're going to move on to matrices and matrix decomposition. And we're going to see a lot of applications of matrices and matrix decomposition, for example, data visualization. And at the end of the talk, I'm going to give you a taste of non-linear operations and non-linear algebra. So what is linear algebra for us? If you actually ask what linear algebra is to different people with different backgrounds, they're going to give you different answers. So if you ask a physicist, if you ask a mathematician or a computer scientist, they're going to tell you different things. And for us, linear algebra really is the mathematics behind operations with vectors and matrices. So whenever you talk vectors, matrices, and in more modern applications of linear algebra, tensors, you are essentially talking about linear algebra. Other concepts which are part of the linear algebra theory are dot products, scalars, projections, decompositions. Sometimes you might have heard reduction or perhaps even embeddings. Those are also words that belong to linear algebra. So if you hear about those or if you read those, it's very likely that you are in a linear algebra territory. And the most important or the most fundamental building block for linear algebra is the concept of vectors. So vectors are sometimes called arrays in the computer science community or in the data science community. It's a bit confusing because sometimes arrays are also used for matrices, but what is not to confuse is the definition of vector and the definition of list. So lists are really just a sequence of objects or numbers or strings or something. When you say vectors, you are implying that you can do certain operations with them, that you can do some mathematics behind them. So let's give a very concrete example of vectors, okay? Suppose I want to represent somehow in our computer my social network account. So on the top, you can see my social network account, and on the bottom, you can see the Data Science Festival's social network account. And to make mathematics a bit easier to do on the fly, I'm going to fudge the numbers a little bit. So I'm going to round the numbers down because I'm going to be doing a little bit of mathematics. So if I were to represent my account as a vector, I could say, for example, I would call this vector V, and I would say that the first entry of the vector is 400, which represents how many accounts I follow. The second entry is 100, that represents how many followers I have. And the third entry would be, I'm going to make up one that is not in the picture, and I'm going to say that the third entry is the number of likes that I have. And I could do the same with the Data Science Festival. Say I'm going to call the vector U, and then this would be 1,000, 7,000, and maybe, again, I'm going to make up some numbers, 500 for the number of likes that they had. This is what we'd call a vector. Some people would put an arrow on top of vector just to represent that this is a vector. I'm going to be just writing the vector itself, and sometimes you might find it in boldface. The entries of the vectors are called coordinates or entries simply, or sometimes in some linear algebra and some data science applications, the entries of a vector are going to be called features. Okay, so I can say that the number of accounts that I follow are features of my account or features of my vector. The interesting thing is that once you represented the two accounts in a vector, you can do some mathematical operations with them. You could, for instance, subtract vector U and vector V, and then you would end up with a vector that looks like, in this case, 600, and then 6,900, and then 470, if my mathematics is correct. And in this case, the subtraction would mean how much more popular the data science festival is with respect to my account. So with one single subtraction, I would have a subtraction between the three numbers of the vector. The other thing you could possibly do is that you could multiply a vector by a number. Say I can double the vector u, and then you would end up with 2,000, 14,000, and 1,000. And if you do these two operations, people say that you are in a vector space. Or some people like to say as well that you are in a linear space. Okay, adding vectors, multiplying by a number, subtracting vectors, those are all legal operations in linear algebra. Whereas if you would do something more funky, like taking the exponential of every entry of a vector, this would not be a linear operation, and you would not be in linear algebra. Perhaps the coolest thing about vectors is that you can represent almost everything as a vector. And the most interesting thing that I found when I was starting my data science career that you can represent as a vector is a text. So for instance, take Shakespeare's plays and take like two very, very famous quotes from two of Shakespeare's plays. And suppose you want to represent those as vectors. What you want to do, or one thing you might want to do, is to get all unique words that are cited in both quotes, and then just count the number of times that they appear in each quote. So for example, for the first quote, the word to appears twice, the word be appears twice, the word or appears twice. Sorry, I'm mistaken. The word or appears once, the word not appears once, whereas Romeo does not appear in the first quote, and neither do any of the other words. Whereas for the second quote, none of the first words appear, so I'm going to put a 0 here, whereas the word Romeo appears 3 times and the other words appear once. Okay, so those are the two vectors that would represent the two quotes in this specific case. And as a matter of fact, texts are very, very, very high dimensional sparse vectors if you represent this, if you use this representation for them. And when we say sparse, we just mean that they have a lot of zeros. Okay, so if you were really to represent the entire works of Shakespeare, you would probably need a vector that has 28,000 dimensions, or more than 28,000 dimensions. And most of the entries would actually be 0. Okay, but it's quite cool that you can actually represent those as vectors anyway. One thing you can do with the vector is to calculate what we call the dot product, or some people call the inner product or the scalar product. Those three are the same thing. And with the dot product, you can do two things. So the first thing is that you can compute weighted sums. And the second thing is that you can compare vectors. You can compare how close a vector is to another vector. So I'm going to show you an example of each of these two things that you can do with dot product. Suppose we have the social network account again, and again, I'm going to fudge the numbers a little bit. Remember, the vector that represented my account was the vector that had 400, 100, and then, if I'm not mistaken, 30, and this was the third entry that I pretended was the number of likes that I had. Now, suppose I want to have a measure of popularity. Say I want to attribute a number, a single number, to my account. So I could say that my popularity P, okay, so I'm going to write popularity here. So I could say that my popularity P is, well, let's think like, what are the most important parameters between the 3 entries of the vector for popularity? Well, maybe the number of accounts I follow, they are important, but not that much. So I could give it a weight of, say, 10%. So I would multiply 0.1 times for 100. But then the number of people that follow me, this is a bit more important for my popularity. So I'm going to give it a weight of, say, 50%. Whereas the number of people that like me, this is really, really, really important. So I'm going to give it a weight of 0.9 or 90%. And if my mathematics is correct, this is going to give me a popularity of 117. So this is just a number that I made up that represents my popularity by weighting the features of my vector. Now, the way we would represent this in mathematics would be to call a vector W. This would be a vector with 3 entries, 0.1, 0.5, and 0.9. And I would say that my popularity P is equal to W, and I use this notation with these brackets, bracket W comma V. Okay, so this is what we call the dot product. And some people just represent it with a big dot, hence the dot product. This is just exactly the same. This is just by definition, this is the same as the formula above. So the weighted sum between entries of two vectors is the dot product. And the cool thing is that I can keep this vector W, and if I had another account, I wanted to calculate the popularity, I could just represent this by the dot product between W and the new account. So this is one thing you can do with dot products. Multiply each entry of the vectors and then sum everything all together. You'll end up with a number. Now, the other very cool thing that you can do with cosine similarity, with dot product, is to calculate similarity. And further on, I'm going to talk about cosine similarity. And I'm going to tell you why we call it cosine similarity. But for now, let's try to represent again the works of Shakespeare into two vectors. And I came up with a third sentence now, just so we can compare different vectors. And the third quote actually has a new word. So that means that I'll have to extend my vector to include the entry corresponding to the new word. But I can again compute the vector for each of the sentences. This will be 2, 2, 1, 0, 0, 0, 0, 0. I'm going to call this V. And then the second one I'm going to call U. This is going to be 0, 0, 0, 0, 3, 1, 1, 1. If you don't believe me, you're free to pause the video and try to compute the vectors yourself. And this third one I'm going to call Z is going to be 0, 0, 0, 0. And then Romeo appears once, the other words do not appear, and the third word appears twice, haste. Okay. Now, if you compute the dot product, say between V and U, remember from the last slide, the dot product is computed by multiplying each entry by the corresponding entry. So I would take like 2 times 0 plus 2 times 0 plus 1 times 0, etc., and just add everything all together. So if I compute the dot product between V and U, I will end up with something that is exactly 0. And the same with V and Z. And again, feel free to pause the video and try to verify that this is true by yourself. On the other hand, if you calculate the dot product between U and Z, you would end up with, well, 0 times 0 plus 0 times 0 plus 0 times 0 plus 0 times 0 plus 3 times 1. And then all the remaining multiplications are just 0. So the sum of all of them would be 3. So the way to read this, the way to interpret this is V and U are completely orthogonal to each other. They are completely unrelated to each other, which makes sense. One of them is from Hamlet, the other one is from Romeo and Juliet. Whereas U and Z have some relation between them, have some angle. I haven't defined angle yet, but there is an angle between them, and they're more similar, or they have some degree of similarity. It's quite cool. You can do weighted vectors using the dot product. You can compute orthogonality or similarity using dot product. And actually any of the other, or many of the other definitions in linear algebra come from the dot product. The norm of a vector, and I'm going to represent the norm with those, with the symbol, the norm of a vector, and sometimes some people put a subscript, norm 2, the L2 norm is just the square root of the inner product or the dot product of a vector with each self. So this gives you an idea of the length of how big is a vector. If a vector is very, very big, the norm is going to be big. And if the norm of a vector equals 1, we say that a vector is normalized. And if you compare two things, two different vectors with very, very different norms, very usually, often you would normalize before comparing them. The angle or the cosine of the angle between two vectors is defined as the dot product between them. If they are normalized, or if they're not, I just divide by the norm. So I normalize them to compare. So this gives a degree of similarity. So if V and U are completely unrelated to each other, this is going to be 0, as in the previous example. Whereas if they have some degree of relationship between each other, this is going to give you a number. And this is what we call the cosine similarity. So theta is the angle between the two vectors, and the cosine similarity is given by the dot product divided by the norms of the vectors. And if you pause the video and come back to the first slide, you're going to see that now you can understand the documentation of the cosine similarity. The most important concept in linear algebra is the one of matrix. Now the second most important concept in linear algebra is matrix. And the simplest way to think about a matrix is if you have two or more vectors and you stack them on top of each other. Okay, so in a computer or in a programming language, you have an array and then you build an array of arrays. And that would be a vector. Now, if you tell this to my mathematician friends, they're going to say this is not exactly the essence of a matrix. Because matrices can do way more things than just being stacks of vectors on top of each other. And I'm going to show you a couple of things that you can do with matrices. So one thing that matrices enable you is to represent computations in a very concise way. So you can actually optimize algorithms and you can optimize your code. So let me give you an example. Remember the Twitter popularity example where I had, say, like a vector that represented my account, which was, if I'm not mistaken, something like 400, 130. Okay, but now suppose that you have loads of those vectors. Suppose you have, like, say, V1 until Vm. And what I also had was a weight vector W, which was something like 0.1, 0.5, and then 0.9. And by taking the inner product between V and W, I came up with a number that represents my popularity. But suppose I have a very huge data set, say the entire Twitter, and I want to compute the popularity of everyone. One thing I can do is I can loop through all the possible vectors and then just compute all the inner products, right? So this is one way of doing that. But I suppose the most concise way of doing that, and the thing that we're going to see on the right is exactly the same as the thing you see on the left, would be to define a matrix which is nothing but V1 until Vm vectors stacked on top of each other. So we would say that this matrix has dimensions m times 3. So each vector has dimension 3, and I have m of those vectors. And if I multiply this matrix by w, I end up with a number p. And I'm going to put the arrow on top just to emphasize the fact that those are all vectors. The thing that you see on the right is really just a representation of the thing on the left. Because by definition, the matrix multiplication on the right is the same as computing the dot product on the left. But the cool thing is that the thing on the right is actually much, much faster. And the reason it is faster is that a lot of people, a lot of computer scientists worked for a long time to try and optimize matrix and vector operations. So whenever you have a piece of code and you can represent this as a vector, as a dot product, and as a matrix multiplication, your code is going to be much faster. So if you actually try to compute the thing on the left, the equations on the left, using a loop, so using a for if you're using Python, it's going to be much, much slower than doing the matrix computation on the right. So matrices enable you to not only to give you better representations of simultaneous dot product computations, but also it enables you to write faster and better code. Like vectors, you can represent a lot of things with matrices. And perhaps the coolest thing that I think is the fact that you can represent images as matrices. Now, I'm talking about grayscale images. Colored images are a little bit more complicated. They are what we call tensors. But grayscale images can be represented by drawing a matrix that has dimensions equal to the number of pixels of the image. Say that this image has m horizontal pictures and pixels and n vertical pixels. You could come up with a matrix that describes the intensity of each pixel. So for example, this would be a number that has, say, value equals to 20. And usually the grayscale intensities go from 0 to 255. So a very, very black part of the matrix would be like somewhere very near 255. Okay, so this would be a matrix that represents this picture. I'm going to call it M. And with this representation, you can do a lot of things. You can do, from simple things like computing the negative of the matrix. For example, to compute the negative of the matrix, you would take the matrix that has 255 everywhere and subtract this by M. Okay, so whatever is 255 is now 0, whatever is 0 is now 255. And this is what we call the negative of a matrix. And this is just a concise representation of the subtraction. But you can do those simple things, but you can also do way more complicated things like deblurring, applying filters to matrices, etc. So this is a very powerful representation of images. And the other very cool thing that you can represent as matrices is user preferences. So suppose you have 4 very distinct TV shows, and you have a couple of users rating those TV shows. So for every TV show, they give, say, a rating between 0 and 5. What you want to do is to represent this as a matrix that has the users as rows and this TV series as columns. So for example, say that user one really likes sitcoms, so it gives 5 to the first TV show, but it doesn't like anything else. Whereas user two is completely different. He just likes crime shows, so he gives 5 to the last one and 0 everywhere. User 3 is a bit more democratic, so he gives 3 to everyone, whereas user 4 doesn't quite like anything, so he rates everything as 1. So this would be the matrix that represents user preferences. And with this, you can do a lot of very interesting operations, as I'll show you next. Okay, so once you represented your data in a matrix, one thing you can do is to decompose this matrix, is to simplify your data. And the idea of matrix decomposition, or sometimes you're going to hear matrix reduction, is starting with a big matrix, potentially very complicated. Say, if you have all Shakespeare works, you're going to have a 28,000 column matrix. How can you decompose this matrix? How can you approximate this matrix to a smaller one that still carries important information and useful information for you? And to do this, I'm going to have to define the rank of a matrix. And to define the rank of a matrix, I'm going to give you an example that hopefully will make it clear what is the rank. So suppose you have a matrix that looks like this. First column is 1, 1, 1. The second one is 2, 3, minus 1. The third one is 0, 0, 0. And the fourth one is 1, 1, 1 again. So this matrix has dimensions 4 by 4. But it's not quite right to say that the dimension of this matrix is 4. And the reason is the third column is just zeros. It doesn't seem to contain any information. Whereas the last column is 1, and it's exactly the same as the first column. So it seems as though these two columns are redundant. So if you were to treat this matrix as a data set, for instance, to run a machine learning algorithm, the first thing you would do would be to drop those columns and then represent this as a 4 by 2 matrix that looks like this: 1, 1, 1, and 2, 3, minus 1. Okay. And the reason you do this is because the last two columns are redundant. And that is the rank of a matrix. So the rank of a matrix is the maximum number of columns that are not redundant. So you can drop redundant columns and still end up with something that has exactly the same information. And in linear algebra, when it comes to matrices, the name of the game is to approximate a matrix by smaller, simpler, or lower rank ones. And there's a very famous result that actually says that every matrix can be approximated by a sequence of lower rank matrices. This is called the singular value decomposition, or SVD theorem. I won't have time to describe exactly what the theorem does, but essentially it's a way to remove redundant columns, or remove almost redundant columns, and end up with simpler matrices that contain almost the same information. So some people talk about the truncated singular value decomposition. For instance, if you have a text with 28,000 columns, you can reduce this, for example, to a 2-column matrix. So you can actually plot your data and visualize your data. And if you centralize your data and apply a singular value decomposition, this is what is called PCA, or principal component analysis, which is a very, very famous algorithm in data science as well. And the other use case, the other very useful use case of matrix decompositions, besides visualizing your data, is to recommend content. Okay, so if you remember the matrix that represented the preferences of our users, with respect to TV series, for example, user 1 liked the first series, and then user 2 liked the last series, user 3 kind of like liked everything, and user 4 didn't quite like anything. And if I call this matrix M, one thing about this matrix is that if you have a lot of users, say if you have 1 million users, this is going to be a huge matrix that is going to be almost intractable to run any machine learning algorithm or to do any prediction on. So what people usually do is to approximate this matrix by a product of 2 smaller or 2 lower ranked matrices. And I'm going to call those P and Q. And if the original matrix had dimensions, say M times N, so you had N users and N TV series, the resulting matrix P will have dimensions M times L, and the second one will have dimension L times N. And you can convince yourself that this is correct using the rules of matrix multiplication. And L is what we call the size of a latent factor. And typically L is much smaller than M or N. So that will enable me to represent my data in a more compact way. And the cool thing you can do with this is that even though the matrices are smaller, you can still predict, or you can still approximate the rating that a user would give to a TV series by using the 2 latent factors. And if you're interested in doing this in Python, there's this very cool package called Surprise that implements just what I described with some extra details that you can probably read in the documentation. So far, I've talked a lot about linear algebra and linear operations and dot products and matrix multiplications and all the things that we can do with those. But actually, many of the operations you're going to find in data science are not linear. Even though those operations are not linear, it is very important to have a fundamental knowledge of linear algebra to understand those things. So I'm going to describe some of the most interesting or the most important or perhaps the most popular nonlinear algorithms that you will most likely encounter during your data science life. I've talked about how to reduce dimensionality by eliminating redundant columns from a matrix. But actually, there is a more involved and a more interesting way of doing this that usually performs better on real data. So instead of just working with matrices and vectors, you can do some nonlinear operations in a data set, and then you can reduce the dimensionality to say 2, so you can plot in a graph in a very efficient way. So those algorithms, they learn a function of the data set that is not linear. So they're able to reduce the data set, to reduce the number of features by finding non-linear latent factors, if you like, of your data set. Another very important class of nonlinear algorithms, which is very, very popular, are neural networks. So the essence of a neural network is to get an input data set, to do some linear algebra with it. So to do some dot product, to do some weighted sums and matrix multiplications. And then after that, a neural network will typically compute a nonlinear operation of the output data set or the output numbers. So for example, a very typical thing that a neural network would do is a dot product, say between a vector and a weight vector, and then compute the exponential. I'm going to denote this by x, the exponential of a dot product. This is a very typical operation. So this enables neural networks to learn not only linear relationships between data points, but also non-linear relationships within a data set. And then there's a third class of algorithms, which are very, very popular, but are very different from matrices and vectors and typically linear algebra operations, which are tree-based methods. So if you hear about gradient boosting, tree methods, perhaps random forests, those do not typically use the linear algebra operations that I described today, and you would need to have a completely different terminology to understand them. And that's it. I hope you enjoyed this talk. I hope it was informative for you. If you have any questions about linear algebra or anything else, do get in touch with me. And I hope you enjoyed the rest of the summer school.